Hello, and welcome to Aviatix Secure Cloud Networking Tech Talk. So today we have an important topic to discuss, and it is about providing additional layers of security to the enterprise applications deployed in AWS. So as you guys know, providing advanced security is extremely critical, and especially when these applications are mission critical applications and sitting on the public facing side of it. So when you design your network, you should always use layered security and defense in-depth principles. For that, there are some tools provided by CSPs, but then you should also consider next generation firewall to provide deep packet inspection and additional layer of security. So by designing and deploying next generation firewall, it's very complex and difficult from day zero and even from day two perspective. But Aviatix can actually ease that pain. So we have our solution called FireNet, Firewall Network, that allows our customers to seamlessly integrate next generation firewall for their workflows or for their packet flows using a policy-based approach. So today I have Rahim with me, who is Principal Solutions Architect at Aviatix. He joined us from AWS a while ago, and he has actually designed and architected very complex, large networks, including the next generation firewall for the customers. So when you look at Aviatix, Aviatix is the leader in providing secure cloud networking. And the businesses and enterprises that are using our platform, they are getting serious business advantages out of this platform. For example, they are accelerating their migration from on-premise to cloud. They are driving business innovation and growth for their businesses with the control and visibility and efficiency provided by the platform. So in essence, they are reducing the risk with this improved feature set provided by Aviatix, including the segmentation, multi-cloud segmentation, audit, governance, and control. The platform abstracts all the complexity of single cloud or multiple clouds away so that you don't have to worry about knowing what's happening under the hood from the networking and security perspective. And in the process, we are actually bridging the skill and talent gap that is out there. Now, when you look at the footprint that we have enabled, there are very large enterprises out there using our platform. And what you see on the screen is just a subset of it. And they are actually present from all different verticals across the globe. So when you look at the architecture, you notice that it is actually driven directly from the Aviatix controller. So Aviatix controller is available from the CSP marketplace. So that actually becomes your entry point into the cloud management, cloud automation, and cloud control. Controller is the one that is driving all the necessary automation and control for single cloud or across multiple clouds by providing a hub and spoke architecture using Aviatix data plane. So in essence, when you deploy this architecture, you get secure, consistent networking and automation. And not only that, you get consistent visibility and control across the board. So today we will talk a little bit about the Aviatix firewall network or FireNet solution, and then we will dive deeper into the Ingress deployment model for the public-facing applications. Towards the end, we'll look at the packet walk and the visibility that is provided by the platform, and then we'll wrap up this session afterward. So with that, I'm going to stop my share and hand it off to Rahim.
So let's get started. Hello, everyone. Thank you for joining today's session. This is a 300 level session. Just to level set, we'll start with the different traffic patterns that customers talk to us about. We'll start from left to right. And the first traffic pattern is the EastWest traffic pattern, which customers consider a traffic that is happening between different environments. And those different environments can be composed of different VPCs, for example. And these VPCs can be in a single region, or these VPCs can be across region as well. The smallest units generally of different trust models had been a VPC. until recently when AWS announced the more specific routing feature. And now inspection can be enforced between subnets within a VPC as well. I've seen very less customers that kind of design different subnets within a VPC with different trust models, but generally the smallest unit of inspection or trust level is typically a VPC. It's interesting to see the intercloud traffic is also categorized. We categorize that as an east-west traffic, although sometimes this traffic is not actually going, is using the on-prem to go between clouds. And that can be, your direct connects or your express routes or Equinix Fabric that you might be using as an underlay. So when we look at the east-west traffic, and even when working with the financial customers, what we have seen is that many times the customers are more interested to kind of inspect that traffic to see what are the different traffic patterns, look deeper into the traffic that's going through and get that level of details rather than doing some enforcements. As far as enforcement are concerned, what we have seen is that if there is any enforcement that customer do require, then that's typically L4 or 5 tuple based rules that customers want to deploy. So although the next generation firewall can perform the east-west traffic inspection, which I think it's a kind of overkill. As far as Aviatix is concerned, if you're interested in just the traffic visibility piece, and if you've deployed the Aviatix Transit solution, then Copilot can give you that inter-VPC traffic visibility through the records that are exported, network records that are exported by spoke gateways and transit gateways. And if you were to look at do enforcement, like for example, 5 tuple inspection, then in that case, we have Aviatix has this L4 stateful firewall feature that you can use. We have also seen customers deploying cloud native firewalls other than the typical cloud native constructs, for example, the security groups and NACLs, that customers have gone towards evaluating cloud native firewalls. And the reason being is because the security groups and the NACLs have a smaller quota, for example, the number of entries that you can have. Moving on to the north-south traffic, that's the traffic that's happening between the data center and the cloud. And it can also include branches that may be connected via IPsec or even via SD-WAN. For this specific traffic, we do see that customers want to inspect this traffic. And next generation firewall, I have seen places where next generation firewall is deployed in there. But just keep in mind that having a next generation firewall in the north-south traffic pattern means that as you scale your north-south bandwidth, for example, if you go from a 10 gig to a 20 gig circuit or whatnot, you also have to think of increasing the bandwidth on the next generation firewall. So it would be better to kind of inspect that traffic only if it is required. Internet ingress is the piece that I'll come to. The last piece that is there is internet egress. Internet egress is more about users or machines that are trying to access web. When I say users, I mean users that are VDI users and they are trying to access internet. And in that case, and even when instances like EC2 instances are trying to connect to some repositories to get patches and whatnot, it makes, and typically the requirements there are more towards, what specific URLs you are allowed to access or what specific FQDN sites that you are allowed to get to. And in that specific scenario, Aviatix FQDN egress scenario or egress solution is the one that can be useful to address this use case. The next generation firewall may be an overkill for machine accessing specific repositories, but for VDI users where you have lots of VDI users and you want to do traffic inspection, not just based on the URLs, but you want to go deeper inside the packet. For example, if you want to see if Facebook posts, for example, are disallowed, but viewing is allowed. If you want to get into that level of detail, then next generation firewall will be required. Coming to the internet ingress. Internet ingress is the piece which is the most used piece where you want to beef up the security as much as possible, and you want to build the defense and depth, and not just rely on features such as advanced shield or WAF, you also want to have a next generation firewall in the data path to protect the public facing apps that you have. And this is the core of our discussion today that we'll be doing. And the rest of the presentation, after we cover the introduction of FireNet, we will basically focus on this internet ingress piece. So Aviatix Transit Finite. Transit Finite is a solution that we deploy in the Transit VPC. Transit VPC, just for those who are new to this, is a VPC that facilitates communication between on-premises to cloud and between east-west environment as well. And this becomes the natural choice to deploy the next generation firewalls to. So the next generation firewalls through our controller are deployed in the Transit VPC. And when you deploy these firewalls, you can then enforce policies and you can selectively say, okay, this is the specific traffic pattern that I want to inspect. And you can configure that using UI, or you can also use Terraform for that. These firewalls that you deploy are deployed in by the controller, but they are deployed in active-active fashion. So you don't need to have any sort of IPsec or BGP running between the next generation firewalls and the transit gateways. And one of the things is that any of the route orchestrations that need to happen, like for example, even the routes that needs to be programmed on the next generation firewalls themselves can be configured, can be orchestrated using the controller. The controller has the vendor integration with most of the popular vendors out there, and we can program the routes. The transit gateways in this scenario will do the hashing of forwarding the traffic to those next generation firewalls as soon as the traffic comes through. And that hashing can be done based on the 5-tuple or can be done based on 2 tuples. The next generation firewalls also perform health checks on these next generation firewalls. The transit gateways do the health checks on these next generation firewalls to kind of check the sanity of these firewalls and check the availability of these firewalls so that they can hash the traffic towards them. This architecture is a common architecture that can be deployed across multiple regions within AWS and can be deployed across multiple clouds as well.
So Rahim, one question I see on the panel here is about deploying or ingesting existing firewalls. So you mentioned the controller can actually deploy these firewalls, which is great. But what if a customer has a private offer or has an existing firewall deployed?
That's a good question, Shazad, and I see that coming quite a bit. So we can ingest existing firewalls within the Transit Finite solution, but there are certain conditions that that deployment has to meet. For example, if you're deploying these firewalls, then these firewalls need to deploy in 2-arm mode, means they need to have 2 interfaces, one untrusted and another trusted interface. And those interfaces should be mapped to the subnets that the Transit VPC deploys as part of this Transit Finite solution. So you have to kind of deploy these firewalls through automation or through UI, whatever your method of deployment may be, but your interfaces, the firewall interfaces, should be tied to specific subnets that we require.
Perfect, thanks.
So moving on, there is another deployment model here where we can do the same deployment model, but in addition, what we do is we have a checkbox when you are doing that in the UI to enable gateway load balancer. This gateway load balancer is the AWS gateway load balancer. And if you select AWS gateway load balancer as part of enabling Transit Finite on your Transit VPC, then we'll not just deploy the gateway load balancer, we'll also deploy the gateway load balancer endpoints as part of the solution. And the gateway load balancer will then be doing the hashing towards the next generation firewalls and the next, and also doing the health checks on the next generation firewalls as well. So this is a pattern that will allow you to deploy the next generation firewalls, and there will be no SNET required on the SNET or DNET required on the firewalls as well. And one thing to note here is the gateway load balancer supports what we call, when you deploy this solution and you deploy this solution and enable egress, for example, internet egress on this Transit Finite, then we support the 1-arm mode only for this specific deployment.
All right. So one question I see again is about the integration with the firewall vendor management tool, for example, Panorama or Checkpoint Security Manager. Is it mandatory, or can your controller control the individual firewalls as well?
So this is an interesting question. So if your Transit Finite has a fewer number of firewalls and you can manage the security policies on those firewalls on an ongoing basis without using that centralized platform, then the Transit Finite, then that we don't have any binding of having a centralized firewall management system, for example, Panorama. One thing we also have seen is that when customers deploy these Palo Alto and next generation firewall resources, they treat these resources more of disposable resources. And if they want to replace an existing firewall with a new one, they can do that. And while doing that, they can bootstrap with the newer policies that you have. So that is one of the patterns that we have seen as well. So it is not required to have a Panorama and Checkpoint Management Server, SMS, what they call, to deploy the solution. It's more of customer choice if they need.
Perfect. Thanks.
So I see one more question here is that Aviatix gateways can load balance traffic to the next generation firewalls. Then what is the additional benefit of using AWS Gateway Load Balancer? So the reason why customers want to use AWS Gateway Load Balancer is they have scenarios where they want to deploy the next generation firewalls in an auto scaling group. So that's one thing that as part of a Transit Finite solution, we do not support auto scaling group. So gateway load balancers are useful in that specific scenario. And also gateway load balancer is required in some of the deployment patterns that we'll see in the rest of the session. So we'll come to that. So we'll start with the different design patterns. And in all design patterns, as we have seen earlier, that the next generation firewalls are always deployed in the Transit Finite. And Transit VPC is a centralized security VPC in that sense. But with that, while the firewalls are deployed in the Transit Finite, there are 4 different design patterns. So the first pattern is a centralized deployment model, and so is the second pattern as well. The only difference between the two is where do you deploy the front-end load balancer? Does the front-end load balancer live within the same VPC, which is the Transit Finite VPC, or we have this front-end load balancers deployed in a dedicated Ingress VPC? And there are reasons for having one versus the other, and we'll discuss this later in the slides. Then the third model is the distributed model, which by some vendors is also known as the isolated model as well. In this model, the load balancers are deployed in the application VPC. And the last model is the combined model, which is a combination of model number 2, pattern number 2, and pattern number 3. So just to reiterate, in any of the models, the next generation firewalls are always deployed in the Transit VPC, and we call that as a Transit Finite. The different design patterns that we are talking here, or we are talking about the different deployment portals, I'll use this design and deployment interchangeably throughout the presentation, is more about where you want to place the front-end load balancer, and then the deeper details of what difference does it make by deploying the front-end load balancer in different places. We'll discuss those in the remainder of the slides. So we'll start with the first model. In the first model, this is the Transit Finite model, and this is by far the most deployed model. And the reason of this being a more deployed model is because this model is more closer to what people used to do on-prem, where they used to have a DMZ, and in that DMZ, the security was beefed up, the load balancer was placed, the DNS resolutions were being done, all of those specific pieces where anything externally internet facing was done in a very secured way. And there was a lot of integration between the security team and the team actually who's making changes to the DNS entries. So this model kind of is very much closer aligned to that. In this pattern, what we do is we deploy the front-end load balancer. And there could be one or multiple front-end load balancers that you will deploy within the centralized security VPC. And this front-end load balancer can be a application load balancer or a network load balancer, or can be any third-party load balancer. So depending on the type of application, for example, a web or a non-web application, you'll choose those load balancers accordingly. So this load balancer can be used, the single load balancer can be used to serve different backend applications. And one thing to note here is while this is a centralized security VPC, the app VPCs are kind of done in an isolated way, that there is a demarcation, clear demarcation, that the app folks will deploy their backend load balancers and they will take care of their backend instances. This model supports both ALB or NLB or a third-party load balancer in the backend application VPCs as well. Now, what needs to be done is we need to tie this front-end load balancer to these backend application, right? And the way we do it is through the firewall. So let's take an example of application load balancer, which is the front-end load balancer, and it's serving a few different applications. So what we will do is we'll terminate the TLS session on the application load balancer. And if you want to additionally protect, you can use cloud native other constructs, such as, for example, AWS WAF to protect that application load balancer. And then application load balancer, as part of TLS termination, it will have some rules. So for example, it can have host-based rules, depending on host headers, or it can have path-based rules. And based on those rules, it can forward it to the targets. And the target group in this case would be the next generation firewalls. And while it forwards to the next generation firewalls, it will forward it on a specific port. So let's say port 1, port X will map to application 1, port Y will map to application 2. So we use the port forwarding, like the specific port that we forward to the next generation firewall, as a means to differentiate between applications. And once the traffic is received on these next generation firewalls, which are, by the way, active, and they're deployed in true ARM mode, in the sense that there's a untrusted interface and a trusted interface here. The firewalls will then perform what we call source net and destination net. And with source net and destination net, what it's going to do is it's going to have a FQDN based destination, and it will map the destination to the name, DNS name of these specific backend load balancers. Hence, in this design, we support application load balancers in the backend application VPC as well. So the couple of things here that regarding client IP visibility. If you want to see the client IP in this specific scenario, there are multiple points where we can see it. We can look at the VPC flow logs, and specifically the ENI of this front-end load balancer. We can also view the client IP in the ELB access log. So if it's an ALB, it will show the client IP in its access logs. Or if it is an NLB, then depending on the listener that has been configured, it might show in the ELB access log. If it is depending on the type of load balancer, it may add additional headers. For example, application load balancer by default adds the XFF header. And if the backend instances have been configured to kind of to log this XFF headers, so then the backend instances will be able to show it in the web logs once the specific configurations are done on the backend instances. So we'll be able to see the XFF headers or the proxy protocol v2 headers in the backend instances. Just a note of caution here that proxy protocol v2 can be enabled on the NLBs, which is the front-end NLBs, but you have to make sure that the applications actually can ingest and support that proxy protocol v2. It's known to break applications, so you have to do application testing before you enable proxy protocol v2 on any of your production NLBs. Apart from this, there is one more feature that exists on the NLBs. The NLBs perform what we call client IP preservation. So if an NLB and the instance that are part of the target group reside in the same VPC, and in that case, the NLB can do what we call the client IP preservation. So in that case, if this was an NLB, then the next generation firewalls will be able to see the real client IP as part of the packet, as part of the traffic logs as well. There is one more important use case that many customers have used, which is to insert a public subnet filtering gateway, which customers can insert using the Ingress routing feature. And just in this picture, it will be inserted between the internet gateway and the front-end load balancer. And what that public subnet filtering provides is visibility of the client IP in Copilot. And Copilot, I know that most of our customers use, and they heavily rely on Copilot to get the visibility of all the traffic patterns. So with introducing a public subnet filtering gateway, they'll be able to see real client IP in the Copilot. That will also help them to enable features like Threat Guard and Threat IQ. What that does is the traffic that's going through the PSF gateway is matched against some database that we get from Proofpoint, and it lists all the malicious and known bad actors. So if we see any of such traffic that's traversing through the public subnet filtering gateway, then we can alert at the minimum to the admins that are managing this platform, Aviatix platform, or we can also, if configured, block that traffic at the source.
Cool. So Rahim, one question I see here is about using this design pattern for east-west, north-south traffic pattern. Is it possible?
Yes, Shahzad, that's certainly possible. You can use the same design pattern to do all sorts of inspections. The only thing that you need to make sure is about two things. A, you have to configure the inspection policies on the Aviatix controller to match what you need to do. So if you want, you just need to configure the inspection policies such that you'll inspect that traffic. The way inspection works in finite design is you can select a VPC and any traffic to and from that VPC will get inspected. Similarly, you can also inspect any traffic that's coming from on-prem. So A, you need to take care of the inspection policies, and B, you need to be careful that if you are increasing the traffic that's going towards your next generation firewall, then you either scale up or scale out your next generation firewalls to ensure that they will be able to handle that additional traffic load.
Perfect, thanks.
A few more things is that do you do TLS inspection on the firewall or not? So that is an interesting one. If the firewall supports, we recommend doing TLS decryption. And the reason why is that it helps the next generation firewall to do deeper packet level inspection and deeper packet level policies as well. So you might be doing using a front-end load balancer, for example, ALB, and you will do a TLS termination on the front-end load balancer, and you will send the traffic towards the next generation firewall with a private TLS certificate, and you can do that as well. So that's something that's useful. In terms of segregation of policy duties, it's important to note that these front-end load balancers can be managed by a separate team. And there's a lot to do here because there is configurations that needs to be done on the front-end load balancers, which includes the listener configurations, the target group configurations, the specific port that you will forward a specific application to, and also DNS records that you will do, public DNS records for the backend applications. So that's one thing. The security policies is another thing that needs to be managed, and that may be the same team or a separate team. The team that manages the backend instances and the actual app, they will manage the backend instances and the load balancers, so that will be a separate team. So generally what we have seen is the application team will deploy their application, they will deploy their load balancers, and then they will communicate through tickets to the team that will be responsible for publishing their app. So and they will provide the CNAME or the DNS name of the backend load balancer to the team that will go ahead and then make this application public for them. So there is a clear demarcation, and there are two different teams that are working in play here. Moving on, this is a second design pattern, and this pattern is becoming very popular. And this is one of my personal favorites as well. And we go over the reasons of why this is a more cleaner design in my aspect and understanding. But let's start covering some of the basics here. This design itself covers both public web and non-web facing apps as well. In this design, what we do is we have a dedicated Internet Ingress VPC where we deploy these front-end load balancers. And these front-end load balancers will target the target groups themselves using IPs. Hence, since these IPs have to be static, hence we can only deploy backend load balancers that do not change IP. So this would be the NLBs, or they can be the third-party load balancers. As you would know already, application load balancer can scale up, and during that scale up event, it can change its IP. Hence, we cannot support an application load balancer in the application VPCs. So the front-end load balancer will tie to the back-end load balancer using IPs, and the front-end load balancer can also support additional security parameters or security mechanisms, for example, AWS WAF, if it's an application load balancer. The thing that I kind of like here is that there is no dependency of publishing a new app that you have to add any sort of ports on the next generation firewalls. The next generation firewall, for them, the traffic between the dedicated Internet Ingress VPC and the app VPC becomes an east-west traffic. So if you look at that, the traffic will go from the front-end load balancers will hit here on the transit VPC. And if this dedicated Internet Ingress VPC is in the inspection list, then the traffic coming from this VPC will be sent to the firewall, will be inspected, and will be sent back to the application VPC. So from a firewall standpoint, you don't have to do any sort of BGP, IPsec, or even NAT configurations. There is no port level isolation that you have to do on a per application basis. So that makes it linear from a deployment standpoint. The security team can just manage the security policies, and the team that wants to publish can publish it. Now, moving on, there is the one cool feature about this is that the front-end load balancers can be deployed by the same team that's actually deploying the application. So think of it that these applications are deployed, and these applications may sit in a specific account. You may want to configure this Internet Ingress VPC in a centralized networking account, or a centralized security account, or any other centralized account. Now, what you can do from that account is you can share the subnets using a resource access manager to the application VPC. And what that provides is that the app owner, for example, if I'm an app owner here, I will start seeing the subnets from the dedicated Internet Ingress VPC in my account in the same region where it's deployed. And I can deploy a front-end load balancer in my own account. So that front-end load balancer, although it shows in this VPC here, from an account standpoint, it stays within the application account. When it stays within the application account, then all the publication of that application, for example, the Route 53 DNS records, can be managed by this team independently. So if you think of agile fashion, this application team can deploy all the components of this application with any pipeline, and they can publish this application without depending on any other teams. The only thing that they need to be aware of is that the security policies on the next generation firewall will allow any sort of traffic that will go between the front-end load balancer and the back-end load balancer. Now, in terms of visibility, you have all the different options that we have discussed earlier that you can use to get visibility to the client IP. And also, since all of this traffic is passing through the spoke gateways and the transit gateways, all of this traffic will be visible via Copilot.
Right. Rahim, I think it's also important to mention here is that with this pattern, we have a selective seeder exclusion feature, which is very helpful for some customers.
Yes, yes, thank you for bringing that up. I actually missed that on the previous slide. So just to expand on that, what is selective seeder exclusion feature? Typically, what you do is when you configure an inspection policy on a controller, you will configure, okay, which specific VPC do I want to inspect? So let's say you want to inspect this dedicated internet ingress VPC. Then what it will do is it will inspect by default all the traffic that's coming from this specific dedicated internet ingress VPC to the transit. What you can do is you can selectively exclude specific siders if you want to, so that those specific siders are not inspected. So let's say if you have shared subnet number 1, 2, and 4 with the app team, and that's where the front-end load balancers are deployed, then you can selectively select those 3 subnets, and only traffic from these 3 subnets will be inspected, because you can exclude the rest of the subnets. Moving on, we come to the distributed design. The distributed design is where you want the application enforcement, the next generation enforcement, the next generation firewall looking at the packet and doing some enforcement within the application VPC. So if you want to have such a deployment pattern, then you are limited with this deployment, where you will deploy the next generation firewall in the security VPC, but you will have to deploy that with gateway load balancer. So this is one of the use cases and question being asked earlier, that why do you need a gateway load balancer? So one of the reasons to have the gateway load balancer was to do auto scaling. The other reason was to support the distributed or the isolated design model. Because the way this model works is the gateway load balancer is deployed in the centralized security VPC, but to send traffic to the gateway load balancer, we need to deploy these things called gateway load balancer endpoints. So as part of the Transit Finite deployment with gateway load balancer, we deploy these gateway load balancer endpoints within the centralized security VPC. Now, if an application team wants to inspect the traffic right within their own VPC, then they will have to deploy a gateway load balancer endpoint. And with that gateway load balancer endpoint, they'll now be able to send traffic to the next generation firewall through that gateway load balancer endpoint. And the way it works is it uses what we call private link, and the traffic will be sent to the next generation firewall, will be any sort of enforcement will be done, and then the traffic can be forwarded to the load balancers and to the target groups. So this is a distributed model. Again, in this model, the firewalls are in active fashion. There is no SNAT, DNAT required. We support auto scaling group here, and all the route orchestrations that have to be done within the centralized VPC and in the spoke VPCs is being done by the our orchestration platform. The moment you insert the gateway load balancer endpoints, you have to do some sort of routing changes, and that becomes that is something that you need to manage on your own. And we have Terraform codes that can help you assist doing that.
Yeah, one more point I want to stress upon is that the importance of the transit architecture, because obviously these applications are deployed here in the Spoke VPC app 1, but they have obviously they're not running in isolation. They need access to some shared services. So in that case, this architecture actually helps you connect to those services wherever they are, maybe in AWS or maybe in some other cloud with our multi-cloud connectivity options.
Yeah, thank you for sharing that, Shahzad. Yeah, that's true that these, and just to double click on that, these instances, they may need to access some shared resources. In order to access those shared resources, they will use the typical the transit architecture here. So there is one more thing that I need to add here is when you deploy the gateway load balancer endpoints, there are some platforms that I know, for example, Palo Alto, they have this concept of mapping a gateway load balancer endpoint to a specific sub interface on the next generation firewall. So what they can do is they can say, okay, gateway load balancer endpoint deployed in app 1 maps to VLAN 10 or sub interface 10 on the next generation firewall. And then they can configure this sub interface in a specific security zone. That helps them build zone-based policies on the next generation firewall. So that is an additional thing that some of the platform may support, next generation firewall may support, and you might want to look at that. We have discussed about the management overhead, but there is one thing specific to this design, and this is that where do you place this gateway load balancer endpoint? Do you place this gateway load balancer endpoint before the front-end load balancer, or do you place this gateway load balancer endpoint after the front-end load balancer? So there are two different design patterns here. So one is called ingress routing, and in this ingress routing, we place the gateway load balancer endpoint between the internet gateway and the front-end load balancer. So you will configure a route table, and in this route table, you'll have the ELB subnets, and you'll have a route entry which says that in order to reach the ELB subnet, go via the next gateway load balancer endpoint. So that's the route entry that you will create, and you'll associate that route table and build an edge association with the internet gateway. With that, what will happen is when the traffic comes from the web, it will go to the IGW, then it will send it to the gateway load balancer endpoint. The gateway load balancer, you can think of it as a kind of a hyperloop where it will send, the traffic towards the next generation firewall, towards the gateway load balancer, which will be received here, and the gateway load balancer will then send it to the next generation firewalls for inspection. And after the inspection, the traffic will return back and will show up again at the gateway load balancer endpoint. From there, it will be sent to the load balancers, and the load balancers will then forward it to the target. So with this architecture, few things that you have to be you have to keep in mind is that this architecture exposes the next generation firewall as your first line of defense within the VPC. So, and what I mean by that is that you might be using some CDN, for example, Akamai or Cloudflare or CloudFront, and that may be a web-based application. So there are some security features that will come into play there, including AWS WAF that can come into the play there as well. And Akamai also has its own WAF. But once the traffic hits the VPC and it goes from the gateway in IGW, the first thing it hits is the next generation firewall. And this means the next generation firewall will see all traffic. So if it's a web application and you want to only listen on port 443, but if somebody ends up sending traffic on, let's say, some other port, then the next generation firewall will still be able to see that traffic. And it will have to receive that traffic, and it will have to drop that traffic if your security policy is configured to do so. And in doing so, you will have to have a higher capacity of the next generation firewalls because it's receiving all the traffic. Now you can do TLS termination on the next generation firewall to look deeper at the packets and then apply deeper application level policies. The one positive thing out of this is that next generation firewall will see the real client IP as it comes by. And in terms of client IP visibility, I have listed some of the things that are there. This is one design which is called the ingress routing design. The other design is the more specific routing design. Both of these designs come into play in the distributed design or the isolated design model. The more specific routing, what we do is we leave the ELB as the first point of contact for the traffic that's coming from that's entering inside the VPC. And then the ELB will listen on the listener port, will terminate valid sessions. And after termination of the session, they will send traffic to their backend instances, and their backend instances will be the targets. But we will configure what we call a more specific routing table, where we will say in the subnets that if you want to reach these targets, you have to send the traffic to the gateway load balancer endpoint. And that's where the traffic will reach to the next generation firewalls, will get inspected, allowed. If allowed, will be returned back, and then it will go to the actual targets. In this specific scenario, what will happen is the next generation firewall will only see the traffic that's filtered by the load balancer. So it will not have to take additional loads in that sense, and only the valid traffic which has been terminated, which has been received on these reverse proxies of the load balancers and are being forwarded to the target group will be seen by the next generation firewall. With this architecture, you have to keep a few things in mind. If you are using an NLB and you have a gateway load balancer in between the NLB and the targets, then client IP preservation is not supported. There is another restriction here is that many times you see that when you have a load balancer, when you use a load balancer, then the targets typically want to prevent any traffic that's coming from the web directly to them. So what they typically do is that they configure a security group where they would say, okay, I will only accept traffic from the security group of, let's say, the application load balancer. That's called security group referencing. Security group referencing breaks if you have a gateway load balancer endpoint in the data path. So if there is any sort of hyperplane ENI, whether that's a gateway load balancer endpoint or a transit gateway ENI, security group referencing does not work. That's one of the limitations that you need to be aware of. In terms of client IP visibility, you will be able to see the places that we have discussed earlier. That's not much changes, and I will list the exceptions out there.
Cool. Rahim, we have about 10 minutes.
Okay, I'll speed up here. Combined design is the one which kind of uses the design pattern 3, which is the distributed design that we just discussed, and the design pattern 2, where we have a dedicated internet ingress VPC, and both of these can work in conjunction. So there are customers that I've worked with which had they had few VPCs which required dedicated firewalls, and there were few other applications that did not require dedicated firewall. So they had a centralized kind of deployment for them. So when they moved to a gateway load balancer based design, then they removed the firewalls from these dedicated VPCs, and they started reusing the same firewalls for both these dedicated distributed or isolated VPCs and the ones that are required for the centralized VPC. And what they did was they were using Panorama, and they built security policies using sub interfaces and trust zones and separate security zones, so those security policies can be carved easily. But that's a combined design pattern that can be supported for the customers that they needed. We'll start with the packet walk, and we have chosen pattern number 2 for the packet walk here. So the client is here, and it's trying to access a web application that's being served by this application load balancer. There could be CloudFront or WAF in between, but we have excluded that for simplicity now. There is also, we have shown a non-web application that's in this NLB, just to show that this is also supported. But for the purpose of the packet walk, we'll just follow the traffic path that's going from this client to this web application that's served by this application load balancer. So this application load balancer is configured with a target group, IP target group, and this RP target group maps to this internal NLB. So when the traffic goes from the client, on the web, the source IP of this will be the client IP, and the destination IP, which will be resolved by the FQDN of that you have mapped this ELB to the external ELB public IP. But as soon as the traffic hits the internet gateway, the internet gateway will do the first level of netting here. So it will do the DNAT, and what we know of the EIP of the public IP of the external ELB will be replaced by the private IP of the ELB. That is the first step that's been done by the internet gateway. Then the traffic will reach the ELB. The ELB will do the SNET and the DNAT. So what it will do, it will take the client IP and will replace it with its own private IP. So this is external ELB private IP. That's the source that it does. And as a destination net, what it will do is, because it needs to send the traffic to this internal NLB, it will replace the destination IP with its own external ELB private IP to internal ELB private IP. Now this header will remain the same, source and destination IP header, when the traffic hits the spoke gateway or it hits the transit gateway. Then it will be received on the next generation firewall. The next generation firewall do not need to do any sort of netting, and they will inspect the traffic depending on if they are doing any TLS termination or what level of application detail that they are looking into. And after inspection, and if they allow, the traffic will hit the internal NLB. And once it hits the internal NLB, the NLB will again do a destination net and will replace this internal ELB private IP, which is the NLB private IP, to the instance IP where the traffic needs to be received, and the traffic will be received on and will be served from the backend instance.
So Reem, I noticed that the source here is still the same.
Yeah. So yeah, that's sharp eyes, man. Yeah. One thing is that the NLB is doing what we call, and the reason the NLB is doing client IP preservation, since the instances are in the same VPC where the internal NLB lives, and we have used instance-based target group, which by default performs supports client IP preservation. Hence, the NLB does not change the source IP here and leaves the client IP in this case as is. The client IP is not the real IP, but the client IP here, I mean, is whatever it received in the original packet, it will remain the same, it will
Got
remain
it.
intact.
Perfect.
Okay. So there are a few design considerations that we have to do here. There's okay, that mark, okay, that's gone. So the first thing is, and this is based on different discussions that we have with the customers, is gateway load balancer fixed idle timeout. So gateway load balancer have a fixed idle timeout for TCP and non-TCP flows. And what happens typically is that can create issues for applications that have long-lived flows. So there may be an application that has long-lived sessions, for example, database connections or SAP application, whatnot. They have long-lived sessions, and typically their timeouts for TCP is configured as 1 hour, and that's the same as firewalls. So what could happen is that the session may expire on the gateway load balancer, because there is no traffic gone, which has been sent on that specific session for more than 350 seconds, then any subsequent packets that arrives on the same session will be treated as a new session by the gateway load balancer, and it may end up in a different firewall. And when it ends up in a different next generation firewall, then the next generation firewall may drop that traffic, and that may cause problems for your applications. So there is a workaround that has been mentioned in one of the blogs that's out there, and you can look at that workaround. That workaround kind of alludes to is changing the timeouts on the firewalls and on the client end TCP stack as well.
Yeah, that could be a showstopper for some applications. It's good to mention.
Yeah. Yes, and it's always better to test your applications while we go through these different designs options. It's always better to test real applications, because if you're just using ping or basic SSH and whatnot to test your applications, that your actual applications may fail. So it's better to have a test environment where you can test these applications. And that brings me to the next one, which is also very important, because some customers want to move to a Transit Finite with GWLB to support the different design patterns that we have discussed earlier. But one thing to remember is that the gateway load balancer does the hashing when it's involved in when it's deployed. And when it's deployed, the gateway load balancer only supports 5-tuple hashing. So what it means is that if you are sending traffic to, if you have applications that rely on 2 different channels, for example, let's take the simple example of FTP, where you have a control channel on port 20 and a data channel on port 21. And your firewall is configured with policies that's matching FTP, for example. And if you use gateway load balancer and it performs the hashing, then your traffic for a data channel versus a control channel may end up on different firewalls. And with that, your firewall may start, dropping that packets, and that's what you may not intend, right? And this is supported on Transit Finite, native Transit Finite with 2-tuple hashing, but just be mindful that gateway load balancer currently does not support anything other than the 5-tuple hashing. If you want to do auto scaling of the next generation firewalls, then you will have to rely on the gateway load balancer deployment model. I see that this auto scaling comes up quite a lot in discussions, but the auto scaling comes out in different discussions. But what I've seen in my personal experience is that auto scaling is something that attracts the technical folks quite a bit. But when you talk about commercial deployments, when you scale up the next generation firewalls, you scale out those firewalls, then there are commercial obligations in terms of licensing. So you need to take care of that as part of your auto scaling scripts. And also, what I see is that customers tend to have more predictive workload and predictive, and next generation firewall deployments. And one of the reasons is because even if you were to scale out, that by the time it takes around 20 to 25 minutes for that firewall to get bootstrapped and to be active to receive traffic. So, and by that time, your peak might have already passed through. So auto scaling is a good concept to have, but it doesn't fly very well with firewalls, next generation firewall deployments, in my opinion. There is also something that AWS supports in that sense is called warm pools. So with warm pool, what you can do is you can deploy the firewalls, bootstrap those firewalls. If you want to have some policies pushed through Panorama or whatever, you have all of that done, and you bring that firewall, shut down that firewall. So and keep it in the warm pool. In case if any actual firewall dies, then you can, that warm pool firewall can quickly come to life. So that the time for bootstrapping reduces by 1/3 in my experience.
Right. We have about 4 minutes left.
Okay, so traffic between, so some of the things that we have discussed earlier, I'll bypass that. So for example, the traffic between the gateway load balancer and gateway load balancer endpoint and the gateway load balancer goes to private link. So that traffic will not be visible in Copilot in our design pattern 3 and the design pattern 4. Aviatix Finite has a number of limits of how many firewalls you can support. So there's a limit of 10 next generation firewalls per AZ with a total of 20 firewalls. And I've seen that that's more than enough for any of the deployments that I've seen out there.
Right.
These are some things that we have already discussed related to more specific routing. And one thing that you please, in the same URL that's for the workaround, you please take a note of how the next generation firewall handling is done with AWS Gateway Load Balancer without reading through. I'll just highlight the key things here. For the existing floors, if a next generation firewall dies, then for existing floors that are going through that failed next generation firewall, then Gateway Load Balancer will continue to send traffic to the failed target until the client resets the session himself. There is no other mechanism in here. If you compare that with ALB and NLB, they would terminate an existing flow and they will send a reset signal to the client, but not in case of Gateway Load Balancer because it's a pump in a wire. For new flows, there's a time that Gateway Load Balancer adds around 50 to 60 seconds after it has seen that the target is flagged unhealthy. So in order to summarize, they have given this kind of ballpark numbers that if you have 10 firewalls and one of your firewall goes down, you're looking at an impact of 20% of the flows for up to 70 seconds. So if you have, let's say, 2 firewalls, then that may relate to 50% of your traffic flows going down for 30 seconds. So be mindful of that. In terms of visibility and compliance, Copilot is the platform that is used by all our enterprise grade customers because it provides you not just the visibility for troubleshooting, but also gives you visibility in terms of trends, where you can look at trends and do capacity planning for your next generation firewall. So in this example, I have filtered based on the private IPs of the load balancers. And I can see that from the front end load balancers, these are my front end load balancer IPs, to my back end load balancer, what is the traffic pattern looking like? So that kind of gives me a pattern of which of my applications are more used and which are being accessed more in terms of traffic patterns, and also gives me a view of what is the total traffic that my next generation firewall is inspecting just for the internet ingress.